Alright, here we are, 5.60, number 1. Anti-differentiation using substitution. Alright, so we're going to use an idea of substitution in order to find the integral of some more complicated functions. So this class opener piece, why don't you just go ahead and fill each of these out and check your answers with mine. I'll put them up in a moment. Okay, so check your answers with the ones I've got here. Looks like I forgot to do the last one. That'd be Fundamental Theorem Part 2. Okay, here's a couple of examples. We're going to do a substitution. To find an antiderivative, we must have our function look like one of the functions we know. If not, then we will need to make a substitution. This is not quite what we are used to integrating. Okay, so what if I wrote this as e to the u? All right, would that be easy to integrate? Sure, it would be. So what I'm going to do is I'm going to set u equal to 3x, and then I want to find du dx. And I'm going to find du dx, which would be 3, and therefore du would equal 3 dx. Okay? But notice I want to replace dx, so I want dx alone. So I would know that 1/3 du equals dx. Okay, so I've replaced e to the 3x with e to the u. I've replaced dx with 1/3 du. And so now what is the integral of e to the u? Well, it's e to the u. So I'm going to have 1/3 e to the u plus c. I have one more substitution to do. It's to substitute back in for u, and u was 3x. If I took the derivative of this, I should get e to the 3x. Okay, likewise in the second one, I'm used to integrating cosine of something. Right, not used to integrating with the opposite of a chain rule, so I'm going to set u equal to 2x, negative 2x. So du dx would equal negative 2, but I want dx all alone, so du would equal negative 2 dx, and negative 1/2 du would equal dx. So I can do a direct substitution by putting in negative 1/2 du. Okay, so the integral of this, what's the integral of cosine? Well, it's sine. But I have to do a substitution back in, and u was negative 2x. If I took the derivative of this, I should get cosine of negative 2x. Alright, so how about in a more complicated situation? So in a situation like this, my first hint would be take the highest power expression and work with that as your u. Right, so I'm going to call u 5 plus 2x cubed. So du dx is equal to, it looks like 6x squared. I want dx alone. Well, almost alone. Check this out here. I see 2x squared dx. 2x squared dx. Do I have a 2x squared dx embedded in here? I do. Look at that. So I'm going to bring this 3 over to this side. So 1/3 du will equal 2x squared dx. I'm going to do a direct substitution of 1/3 du for these items. So this would be 1/3 the integral of the square root of u, right? I did a substitution, times du. Okay, so I can integrate that relatively easily. That would be u to the 1/2 du. Alright, so if I integrate that, I'm going backwards, so I'm going to add and divide. Okay, so let's do a little algebraic manipulation. That'd be 1/3 times, take the reciprocal of this, 2/3 u to the 3/2 plus c. One more step. Let's combine like term or multiply these. So that would be 2/9. And what is u? U is the square root of 5 plus, it's not going to be the square root anymore. Sorry. It's 5 plus 2x cubed to the 3/2 power plus c. Okay, so I want to make a point here about this one. I want to take the derivative and prove to you that the derivative equals the original. Okay, so I'm going to take the derivative of what I have here. Alright, so the derivative of this would be bring down the 3/2 and then now reduce the power, and then by chain rule I have to multiply by the derivative of the inside. Okay, so let's simplify this. 2's cancel, I get a 3 down there. 6 and 3 reduced to a 2. So what I'm left with is 2x squared times the square root of 5 plus 2x cubed. And I believe that's what we had. Yep, got it. Okay, let's move on. I'm going to erase a little bit here. Give me some space to work. Okay, don't forget plus c. You get your question wrong if you forget plus c. Okay, this is funky. This is a weird one. Alright, but I'm going to do a little change here and it might scare you a little bit. This is actually a definite integral. So we're going to have to do a little bit of algebra at the end. But I'm going to write this as secant squared 5x. 1 over cosine is secant, so 1 over cosine squared is secant squared. Alright, so I'm going to set my u equal to 5x. So that means du dx equals 5. So that means du equals 5 dx. So that means dx equals 1/5 du. Okay, so what I can do is I could do a direct substitution of 1/5 du in for dx. And I can also substitute u in for 5x. So really what this has become is pi over 6 to pi over 4 of secant squared of u times 1/5 du. I like to bring that constant out in front. Okay, so what is the integral of secant squared? Well, it's tangent. Okay, and I don't need plus c because this is a definite integral from pi over 6 to pi over 4. I'm going to evaluate off camera and let's see if we get the same answer. Okay, one quick thing. U is 5x. Make sure you switch that back and then work with evaluating your definite integral. Alright, so I did some evaluating here. I think I did this correctly. As I plug in pi over 4 and pi over 6, I get 5 pi over 4 and 5 pi over 6. The tangent at each of these values, tangent of 5 pi over 4 is 1, and tangent of 5 pi over 6 is negative 1 over root 3. Alright, so then I do a little bit of work here algebraically, and I get this value for that integral, and its area under the curve on that interval. Alright, let's do a couple more. Alright, and again, another definite integral. I would set u equal to secant squared. Nope, I wouldn't do that. I would set u equal to tangent x, because du dx is secant squared x. So du, and it's really nice when this happens, when du comes out to be the exact value that you have in your integral, you should say thank you much, because now I can do a direct substitution there, and all I'm doing is 0 to pi over 3. Tangent is u, secant is du, secant squared dx is du, and the integral of u is u squared over 2. Okay, but it's not really u squared over 2, it is tangent squared x over 2, evaluated from 0 to pi over 3. Okay, so the tangent squared of pi over 3 over 2 minus tangent squared of 0 over 2. Well, this value is just going to go to 0. So we're really just evaluating this. Well, the tangent of pi over 3 is the square root of 3. Okay, so this is really the square root of 3 squared over 2, which would be 3/2. Alright, one last question here. This is a classic. Okay, I see it right away. You want to find the more complicated of the two. I'm going to call u x squared minus 4. This isn't going to work out perfect because we'll have a constant with us at the end, but that's okay. So I get 2x. I'm not seeing a 2x in the numerator, so I know I'll have a constant. So I have 2x dx equals du. Therefore, 1/2 du equals x dx. So I can substitute for x dx, I can substitute 1/2 du. And of course, this would now be the integral, right? X squared minus 4 is now u. So I have 1/2 x dx is replaced by 1/2 du. So I'm going to leave a 1 over u du. So you'll see I've got my 1/2 du. That takes care of x dx. And then the u takes care of x squared minus 4. So the integral of 1 over u is the natural log of u. And u is x squared minus 4. And there you have it. That's our answer. Alright, that's u substitution. Hope it went well. We'll do plenty of practice on that. See you next time.